it has been some time since I've seen you. So tell me a little bit more about what has been happening since.
With my work.
Yep.
Yeah. So actually, we are, in Turkey, we are on the earthquake zone, or there are multiple places in Turkey subject to earthquakes. Mm-hmm. So what we do is that we try to do more or less automatic earthquake management. Now it's done mostly manually. So we gather information from households and then we try to predict actually if there are people in buildings without really becoming invasive. So we don't want to really interrupt with the private life, but we measure water, electricity, and we try to detect from GSM signals or Wi-Fi, but we are not so far yet. Basically, now we try to simulate, and then later we want to collect with real data, and so that we can obtain more data. So mix them together. So then we gather information. So we have a critical infrastructure, which means that we have to be reliable and high performance and so forth. And it should be, of course, secure. And then we do complex event processing. We get the data, process it, and give meaning to it, which means that we are actually saying, for example, this building has been damaged and this bridge has collapsed and there is a fire and so on. All this information we gather by using, things like ontologies and complex event processing and rules and so forth. And then in the end, we decide, and based on that, we generate tasks and resources, and we optimize tasks and resources. And so, in other words, we have a digital twin of the city, and in digital twin, we see what's going on. Hopefully, we also know how many people are under the collapsed building, because it's important. And then we apply, we dispatch to firemen or firefighters or the ambulances and so forth to optimize the aid work, let's say. So this is what we are doing. And there are many uncertainties. You can do, data analysis and machine learnings, self-configuring architectures, and all this stuff you can do because there are a lot of uncertainties. But now I'm giving the talk, and so we reverse the process, right? So,
that
so
makes
I know you a little bit. So actually, you want me to give the talk?
Sure.
No, if I start, I can hardly stop.
No, this is. I just wanted to understand a little bit about your.
Yeah. So maybe we should have really a chat. So it's always nice to talk to you.
It's always nice to talk to you. No,
yeah, so when I talk to you, I'm at least becoming somehow happy. I don't know why, but I think because of the way how you laugh, it makes me happy. Yeah,
that's fantastic. There's very little things I could do.
All right. Now I think I will give the word to Rabia. Rabia should start the process, and then okay. Now we start.
Sure.
Thank you. I am Rabia Bilgici, an assistant student at Smart Cities and Digital Ecosystems Lab. This is the first third of the seminar series organized by Top to the Smart Cities and Digital Ecosystems Lab. The talk will take around 45 minutes. Approximately in every 2 weeks, we will have distinguished speakers all around the world. To introduce our speaker today, I first give the word to Professor Dr. Mehmet Akşit, who is the head of our lab. Thank you.
Thank you, Rabia. I'm really very happy to introduce Professor Dr. Hridesh Rajan. I think in America they will say Rajan, right? Yep. In Dutch, in Central Europe, it will be Rajan. He is a professor and chair of computer science at Iowa State University, where he has been there since 2005. Professor Rajan earned his MS and PhD from the University of Virginia in 2004 and 2005, respectively. Professor Rajan's recent research and education activities are aimed at decreasing the barrier to entry to data-driven sciences to broaden participation. His work on the BOA project is aimed at the invention and refinement of programming languages and cyber infrastructures that democratize data-driven science and engineering, including software engineering. So actually, Professor Rajan has quite a wide scale of interest. So I think what I appreciate very much with him is that he can combine different techniques and more or less put them together in such a form that the whole is much more than its parts. I will not read your whole short bio because it is quite long, but my personal opinion is, as I said, on one hand, Professor Rajan can be quite theoretical, on the other hand, very practical. And as I said, very successful combination of multiple techniques together. I think that's a very, very interesting aspect of him personally. That's what I think. So please go and present your talk. Thank you for presenting this talk here.
Thank you. And thank you, Mehmet. You have always been a very kind mentor from very early on in my career. I remember meeting with Mehmet many, many years ago when I was a PhD student. And since then, we have always met in various conferences and venues. And he has always been very kind and a wonderful mentor. And I really appreciate that. So today I'm going to be focusing my talk on this new line of work that I'm doing on what I call a D4 framework, and D4 stands for Dependable Data-Driven Discovery Framework. So this talk is about data-driven decisions, and by data-driven decisions I mean such decisions that are based on insights gained from acquiring, analyzing, and possibly modeling data. We focus on data-driven decisions because, number one, they are omnipresent and they are being used in many safety-critical systems. For instance, cars are now using data-driven decisions to support autonomous driving. Aviation systems are increasingly using data-driven decisions for a variety of tasks ranging from air traffic safety to TSA monitoring. Medical diagnosis systems have traditionally relied upon data-driven decisions, and that reliance has grown over the years. Data-driven decisions have also made their way into our lifestyle. For instance, it is increasingly common to use voice command, which is the data-driven voice to text conversion system, to control our devices or to play our music. Data-driven image recognition systems are being used to detect whether children are sleeping, awake, or moving. Data-driven decision systems are used by home security systems to determine if there is an intruder or just a stray cat. And the use of data-driven decisions to recommend movies, what to buy, and so on has been a commonplace today. Data-driven decisions are also starting to affect us in subtle and not so subtle ways. So for example, some universities make use of data-driven decisions to select applicants for admission. Increasingly, credit card companies are making use of data-driven decisions to determine our credit worthiness, whether to approve a credit card, and if so, what should the credit limit of the person be. Some companies have developed data-driven systems for selecting candidates out of a larger pool of applicants. The question that we will be concerned about is, what are the ways in which data-driven systems can fail, how to determine whether such failure has occurred, and how to possibly mitigate them. First, let us take a look at some publicly available examples of failures to understand the impact that the failure of data-driven decisions can have on our society. Data-driven decisions can exhibit unfairness. For example, we have discussed the use of data-driven decisions for selecting candidates to interview out of a pool. Recently, one such system was found to be systematically favoring men over women in selecting individuals for technical jobs. Another such system assigned labels to images for consumption by downstream systems. It consistently labeled Black people as gorillas. Accountability is another big concern for data-driven systems. For instance, one widely publicized chatbot made data-driven decisions to determine how to respond to questions. Due to the problem with ingested data, this system quickly started to produce inappropriate answers and promote offensive behavior. Similarly, data-driven systems were used to determine whether a certain aircraft is fit for flying, and failures were ignored as outliers, but it ended up having an impact in real life that cost lives. Uncertainty is another big concern. For example, data-driven systems used in autonomous vehicles make hundreds of decisions about real-world objects. These systems are not 100% certain about these decisions. And this uncertainty has often led to the loss of life and limb. On top of these concerns, transparency has become a major issue. The behavior of a data-driven system cannot be fully understood. Some components of these systems are essentially black boxes that are not even understood by their creators fully. These concerns and other concerns are compromising the credibility of data-driven decisions in a big way. And that is bad because it undermines the trust of the society on fact-based decisions. In some cases, members of the society are already abandoning the use of the data-driven decision systems. For instance, Los Angeles Police Department that used to use data-driven systems for criminal sentencing has since, and has had some success in reducing crime rate, has since decided to eliminate the use of these systems over unfairness concerns. So at Iowa State University, we are very concerned about these issues and believe that foundational research is necessary if we were to maintain public trust in data-driven decisions. Fact-based decision-making is critical to the vitality of the society, and we mustn't let untrustworthy data-driven decision compromise public trust in fact-based decisions. At ISU, since 2017, a group of researchers have started to come together to think about these issues. Investigators range across computer science, statistics, mathematics, application areas such as genomics, transportations, materials, polymer informatics, etc. We have recently received a major National Science Foundation award to further this research and to work towards establishing a dependable data-driven discovery institute. So to define what we mean, let's first define what we mean by dependable. What do we mean by dependable data-driven decisions? We believe that a data-driven decision is dependable when it is produced by a data science lifecycle that is dependable. So if the producer of the decision can be relied upon, then the decision can be relied upon. And when do we call a data science lifecycle as dependable? If there is a basis, if there is a rigorous basis, formal basis for justifiably trusting its output. So let's now define these two terms more carefully. What do we mean by data science lifecycle? And what do we mean by dependable? So a data science lifecycle is a collection of data science processes from problem identification to data-driven actions. So these processes together are referred to as data science lifecycle. So for example, in the graphics, you can see various processes in the data science lifecycle, such as study design, data acquisition, exploratory data analysis, feature engineering, modeling and training, model evolution, prediction, interpretation, communication, decision, action, which might then also lead to problem identification, completing the circle. So there is the data science lifecycle consists of stages, and a stage is a data science process. For example, problem identification, study design, or data acquisition. I tend to think of these stages as collection of communicating sequential processes. Edges represent the flow of data from one stage to another. In our model of data science lifecycle, one stage is not directly controlling another stage. Rather, it may send some data to another stage which might react to receiving this data. So edges are essentially flow of data, they're not flow of control. So we have introduced the dependable data-driven discovery framework to understand and reason about the dependability of data-driven decisions. To ensure that use of the term framework doesn't cause confusion, I wish to clarify that D4 is a conceptual framework and not a programming framework, such as Spring. So D4 is a holistic framework that goes beyond the stages of data science lifecycle that are concerned about predictions, such as feature engineering, modeling, training, and model evolution. And the reason is that we believe that a holistic approach is needed because dependability of the predictive stages cannot be achieved if the stages earlier in the life cycle, for example, experiment design, data acquisition, etc., are not dependable. So in order for the prediction stage, modeling and training and model evolution to be dependable, these earlier stages also have to be dependable. So our framework consists of three pieces, and these are risks, measures, and mechanisms. The entire framework could be thought of as parameterized by different kinds of risks. For example, of a risk includes fairness, uncertainty, complexity, robustness, and freshness, etc. So risk, let's take a look at it more carefully. It's a cause that can lead to failure. So the question here we are considering is, what are the risks to the validity of decision produced by the data science lifecycle? Measures. Measures are a facet of dependability, and measures essentially quantify these risks. How do we quantify these risks? What are the tolerance levels? Mechanisms address the risk associated with measures, how to communicate and measure the risks. D4 framework can be thought of at different levels of abstraction. So the highest level of abstraction is, of course, the algorithmic level, where the application of the D4 framework can be used to analyze richer properties. Then the next more detailed level is at the level of models of the data science lifecycle, where some low-level details are abstracted away, and essentially a model is a graph where nodes are stages and edges are data flow. So we can use the D4 framework at that level as well. And the lowest level of abstraction is actually the software code. And if we think about, if we apply the D4 framework at that level, so the advantage, of course, is that it's closer to the actual functionality of the data science lifecycle. So it's also often possible to extract the model of data science lifecycle from code and then make use of the high level of abstractions to inform the process. So ideally, one can just reason about and apply the D4 framework at this middle model level by making use of the models extracted from the software code and using properties that are applied, that are inferred from the algorithms. To see all of this in action, let's take a look at a case study. So the case study that we're gonna think very carefully about is this TSA passenger screening system. And this passenger screening system, probably all of you are familiar with. You go to the airport and you will go through a detector of some sort, and the detector checks various parts of your body, and then it makes various decisions. The problem here was that the high false alarm rate can create bottlenecks at airports. And so what TSA and the Homeland Security did was they gave a challenge to create a data-driven system that can decrease the false alarm rate. And so this is kind of what the system looks like. so a passenger comes in, and the airline essentially does the first level of screening, where they show identification and so on, and they get ticket, and then they come to TSA, and this black box is really the model. And if the model says low risk, you get a boarding pass and your screening is expedited, you get on a plane. If it says unknown, then you have a standard process through which you go through. If you say high risk, you go through a more detailed process. And if the highest risk, you're not allowed to board the plane. So this is done using this whole thing is done using a software system that incorporates a data-driven decision-making system. So of course, we don't have access to the actual TSA system. So we looked at examples of entries that were done to solve this problem on Kaggle, and we extracted some of those entries. And I'm going to illustrate the rest of the data-driven discovery framework using those example life cycles. So here's an example of extracting data science life cycle from software code. So the code on the left is essentially trying to build a model, and so this is essentially creating an attention layer. These two lines are creating FCN classifier. And then these lines are essentially defining connections between these different layers. And so essentially defining the data flow. So using this process, we can create a model data science lifecycle for this TSA system that kind of looks like this, where you have a raw scan of the person as they're walking through the detector, an X-ray machine. These go through this model, and then the model kind of based on the bar gives 16 different outputs for different parts of the body, and then there's a system that takes the 16 output probabilities and makes a decision whether to flag an individual based on these outputs. So in this system, what is a risk? So in this system, a risk is uncertainty. And why is that a risk? It's because these probabilities that are output by the system, they're not definite answers. There is some uncertainty associated with it. And if the system, when producing its output, is reasonably uncertain, then the output might not be relied upon. So that's a risk to the decision of the system. So then, how do we measure the risk? We measure the risk using the log loss function. So this log loss function essentially measures the uncertainty over the output 1 to n. So just to reiterate, representation of the data science lifecycle, which is one part of the framework, identification of the risk, which is the second part of the framework, and then how do we measure that risk? What's the measure? And this is how we measure. So these three parts of the DS framework, D4 framework, can be seen through this example. Now, we can take this a little further, and we can give a more systematic treatment to this. And in particular, I would like to show you how this could be utilized in conjunction with a weakest precondition based method. And so let's look at this example in conjunction with how it can be utilized for more formal reasoning. Let's look at some notations, review some notations here. So in the following slide, we will be using whole triple, and we will write them like this: P, S, Q, And what this will mean is that if pre-state of a system satisfies P and S finishes, S terminates, then the post state will satisfy Q. So the problem is often, the weakest precondition problem is often, given a code fragment S and a post condition Q, find unique P, which is the weakest precondition for S and Q. So so this is how you kind of define the WP weakest precondition. So our task is, given for a given post condition of a stage in a data science life cycle, what is the weakest precondition? And what we would like to do is to start with the final stage of the data science life cycle and infer the weakest precondition and propagate that backward to see if it's is truly a risk. So if it turns out that that we cannot propagate, we cannot compute the WP, then it may be possible that the data science lifecycle is unable to satisfy the properties that we set out to show. So let's look at this. Look at this weakest precondition-based method in the context of the example that we talked about. So here's this example again. So here the Q, here's a Q. So given a post condition, which is the measure on Q, and the statement, which is the FCN classifier in the model, what should be the weakest precondition right before the FCN classifier? So between the dropout and the FCN classifier layer. And so we can expand what happens here in this box. And so the operation here really is, y equals to, for every input, x equals to x1 to xn, and the output produced y1 to y17. The operation really is y equals to x into weight matrix transpose plus some bias b. That's the operation that is really applied here. Given this understanding of the operation, and given the post condition on y's, we will be able to compute the weakest precondition on x's. That is the input of this particular stage. So the systems are ranked, as I said before, using the following log loss performance measure, where n is the number of predictions. Here 17 is the number of data instances, and yi equals to 1 if a threat is present and 0 otherwise, and yi hat is the predicted probability. And so suppose epsilon is the measure so this is the threshold that is required for the model to be accepted. We essentially, that translates to probability P1 to P17 being less than epsilon 1 to epsilon 17. And so this then translates to uncertainty estimation in the following manner. So again, just to remind you that we have the weight, we have the biases, we have the input, and using these we compute this matrix, which then the matrix value is essentially the P1 to P17. And so the post condition really is then that W1 X1 X2 to plus B1 is less than epsilon 1, and W2 is less than epsilon 2, and so on up to epsilon 17. And so then the weakest precondition is expectation of Xi by solving this system of equations. That kind of gives a very brief overview of how we go about applying this framework in practice. So now proceeding forward, now the weakest precondition of the FCN classifier becomes the post condition of the dropout. So now we apply the same process again. The weakest of the post condition is EYI, expectation that we calculated from here. And based on that, we try to get the weakest precondition. Similarly, we can take the precondition of the dropout, and that becomes the postcondition of the apply attention weight. And I won't be spending too much time on that in the interest of time. But you can see that the ideas are going to be applied in a very, very similar manner. Now this becomes a little interesting because the precondition of the apply attention weight kind of distributes over all the softmax components that are being used in parallel, and for each of these we have try to understand what the operation is, and then based on that we apply the postcondition and the operation to compute the precondition. So that's kind of the summary of how we go about applying this dependable data-driven discovery framework. So let me then summarize my talk. So what I have said to you today is that data-driven decisions are being increasingly utilized in safety-critical systems in our society. The impact of unreliable decisions can be significant, ranging from unfairness to loss of life and limb. I talked about a framework for getting a handle on dependability for these decisions. And the framework gives a holistic approach to thinking about dependability of data-driven decisions. It consists of 3 parts: risks, measures, and mechanisms. Risks are threats to dependability of data-driven decisions. Measures are way to quantify the risk, and mechanisms are ways to mitigate the risk. And I talked about a specific case study where high false alarm rate can create bottlenecks. And we saw how in this particular case study, you can propagate measures of risk from postcondition using weakest precondition-based methodology to create preconditions for various components, and you keep propagating this until you can either prove that the system is going to satisfy the postcondition in all cases, or disprove and show an example of where the system might not be able to meet the necessary post conditions. So that is all that I had for today. Thank you very much for your time. I really appreciate the opportunity to speak with you today. If you have any other questions, any questions at this point, I'll be happy to take them. And I'll leave this slide up just so that maybe we can refer to this at various points in the question and answer process. And thank you again for coordinating this talk, Rabia, and thank you for the invitation, Mehmet.
So thank you very much. So it was very inspiring, and actually it is one of the topics which I'm personally bothering a lot because there have been also a number of publications how terrible we sometimes the systems conclude, like you said, very racistic or discriminating decisions, and very scary, actually. If we are ruled by data, then we can really have very wrong conclusions. So I think it's a very crucial work if we want to continue along this line. So along this line, I mean data-driven living, if we can call it like that. So we should really understand the risks, and that's very important. So if there are questions from the public or the group, then are there questions? Please, maybe people can think. I have, of course, questions because it's a very, of course, challenging topic. So one thing I would like to understand, so do you really do code analysis and try to form models, how to understand how decisions are made? So in your one slide, you showed that you analyze code, and by code analysis, you try to extract the data flow model or the decision model.
Right. So the framework itself is an analytical framework, and it doesn't necessarily. It could be applied, it could be applied by a human being. Human being can do the computation, but we have shown that in some cases, this framework can be applied automatically. And that was the example where we extracted the model from software code and did an analysis of uncertainty over that. So for some kinds of risks, we are able to show the possibility of this automated analysis. But of course, this is not a done deal yet. And for a variety of risk, I'm not so sure that we might be able to completely automate the process. And I think, but there is also this other aspect, so for example, if you think about the data science life cycle, that picture that I have here, there are some subjective things, like, for example, communication, for example, interpretation. So interpretation is essentially, if the life cycle presents you, if the data science life cycle and the systems present you with some chart showing trends, how do you interpret that chart? What's the process of that? And then, how are those communicated, and how are decisions made using what is communicated? And in some cases, this is a very automated process. For example, if you're thinking about in an automated system like a robot, the robot is going to interpret the decision, is going to communicate to the actuator to do what to do and make a decision, and then the actuator will take action. So in that case, it's a very, very automated process that could be understood. But if we think about this as a decision-making process, so for example, some scientist presents the data that this is what is happening across the country in terms of, in terms of, say, for example, COVID cases. And then some policymakers are going to be interpreting that chart, communicating it to the next set of policymakers, who will then be making decisions and then implementing actions. So in those situations, this whole process might not be analyzable, so to speak, although some some models, some approximate models could be constructed based on human behavior and the agent-based modeling of human behavior. But I don't think we have a good handle on that yet at this point. So that was kind of a very long answer. I want to say in short that our ability to completely automate these application of this framework is limited to cyber systems. Whenever we have cyber human systems, the thinking becomes a little bit more complex, if that makes sense.
Yeah, so actually this will be my second question. So the models, and if you can obtain models, and if the decisions are transparent, possibly many decisions are also not transparent, right? So it could be the secret of the company who builds such systems. They don't want to, of course, publish everything. In addition to that, so do you have any idea? Okay, so you formulate this risk, and based on certain parameters, you decide if you fulfill the weakest condition. But of course, you may be mistakes or wrong assumptions about parameters and so on. So there could be also false positives or false negatives even. Any idea? Of course, you tried in your case an example. You have an example. It's a very actually illustrative example. And any idea how reliable is the decision about the risk, or any feedback on that? So another level of, let's say, risk management.
Yeah, so it's kind of like a meta risk.
Meta risk, yeah.
Meta risk. So risks about a risk measurement mechanism.
Yes.
Yeah. And that's a great question. I think that's I really appreciate that question. I think this is a good point. I personally and my students have not thought about this meta level yet. But this certainly opens up opportunities for more work on this topic. I think this is what my hope is, though, that the state of the practice will be advanced by a more formal documentation of what could go wrong.
Okay.
So currently we are at a point where, we just talk about implementing these things. We don't talk about quality assurance with respect to these things. And the act of coming up with identifying, okay, what are the risks here? How do we measure them? When do we know that these risks are within the acceptable boundary? This process itself, if we start to think about that, if we start to follow this process in practice, that itself might have a significant impact on the quality of the decisions produced by these systems. I think that's my intuition at this point. Of course,
absolutely. So I think it should be maybe, I don't know what the consciousness level of people, or maybe the managers. I think this should be more or less a compulsory thing, right? Our life depends on so many decisions, and there should be some, let's say, quality attribute associated to it. And then I don't know how conscious the companies who are working on the system are they conscious about the risk of making wrong decisions, or how conscious? I think very interesting from that perspective. It's also a moral issue,
It's the consciousness vary. So, for example, we interact with some group of companies, namely financial companies, where there's a significant consciousness of this, because that consciousness is guided by regulations. So one has to show that the regulations are being met, so to speak.
Exactly. Yeah.
So there is significantly higher level of consciousness. But then my intuition is that the majority of other places, it's very much a reactive approach. In other words, if something goes wrong, then that event brings the risks to our consciousness.
Exactly. Yeah.
That's so some of these examples that have been featured on the news, there it seems like, at least from what I could glean from the write-up, is that the bad news leads to bringing this to our consciousness. Okay. So that's, again, this is just I have not done any formal study or survey of any companies on this. It's just a very informal observation based on the data that I see.
Even a very, very formal work is 99% informal work and 1% formalism. They say creativity and thinking, and actually we do all the research based on belief that we can solve difficult problems. Thank you very much, Hridesh. So I appreciate very much. It was very nice to see you again.
It was a pleasure to see you again as well. Thank you very much for taking the time.
Yes, and I will put I think we have recorded well, I hope so. I recorded on the cloud for the first time. Before I was recording on my local disk. we will put this on the link in. And thank you very much for presenting. And let's have a chat also in the future, just to talk about our work, because I'm also very eager to present our work to your group or to yourself. Thanks again, and hope to see you again somewhere, sometime.
Yep, same here, and I look forward to an opportunity to for you to visit with us and discuss your work in not so long from now.
Okay, great. I'm looking forward to visiting you, and I also thanked Rabia Bilgücü for organizing the seminar. And bye-bye. Take care of yourself.
Bye.
Bye-bye.
Bye, Rabia. Thank you very much. Bye now.
Yes, sure. Bye-bye.